So this is the overall procedure. Again, in nutshell, we are basically doing structural analysis. And in structural analysis, we know moment distribution method for a regular frame, prismatic case. Cross sections are not changing. In this case, depending upon the boundary condition, my moment of inertia for column is going to change. Moment of inertia for slab beam is going to change depending upon what kind of system that I have. Somehow I have to bring these variations into my stiffness parameters and carryover factors and fixed end. That is what we have discussed how to do that. Okay. And in that process, we invoke several concepts like equivalent column, and then we looked at average stiffness parameters and so on. Right. So now let us see how to run this example. So in this case, you have a 4-span slab system. You have in the x directions, you have 8 meters of 4 spans. In the y directions, I have 3 spans of 6 meters. And it doesn't have to have any beams, and the columns are directly supported. The slab is directly supported on the column. Column dimensions from an analysis worked out to be 500 by 500, right? And you see here, you're also going to have a drop panel. Okay, so it's not a flat plate system; it is a flat slab system. Okay, and because you have 8 meters, so we are providing drop panel. When you go for a post tension system, sometimes without drop panel, flat plate system also may work out if your loading and spans are less. But in this case, you have in one direction, you have a longer span. If you don't provide drop panel, it may have punching shear failure. So we have to be careful about that, which is a two-way shear failure mode. We'll talk about it. So the floor plan of the flat slab floor system for an office building is shown. The floor to floor height here can be taken as 3.5 meter, and all the columns are 500 mm by 500 mm. Let's see now. We are assuming a live load of 3 kN per meter square and superimposed dead load of 2.5 kN per meter square. And it is superimposed dead load, you can see slightly on the higher side. Why? Because we're including finishes, partitions, false ceiling, mechanical and electrical. All of them are included together, right? And we are going to analyze one typical interior bay in the shorter direction. So that is what it is given here. It is highlighted here. This particular frame is what we are going to do the analysis. Okay. So let us see how to do this analysis. So this particular frame, you're going to have. So what would be the width of the frame? For example, on this side, you go half the way up to 4 meters. And this side, I'm going to have 4 meters. So L2 is going to be 4 meters. And L1 is going to be 6 meters. And it is not changing. It's a very regular structure. Okay. And this L1 is going to be 6 meters and L2 is going to be 8 meters. And we're going to assume M30 grade of concrete and Fe 500 grade of steel. Now let's see how to do this. Okay, in a two-way slab design, the slab thickness is always governed by deflection control. Okay, so strength will have, in fact, we have tested some slabs in our lab. Though it is designed for 3 kN per meter square, it will fail at 15, 20 kN per meter square. So you will get tremendous amount of capacity because it's a highly indeterminate system. Okay, but the thickness is actually governed only by deflection criteria. So let's see how to fix the deflection. Now, if you look at your code, the code gives you provisions for flat slab thicknesses. In fact, we have discussed in the direct design method also. If the slab is supported on flexible beams, it does not really give a very good recommendation. So we have to resort to using ACA code provisions or Canadian code provisions. Now, for the flat slab, the code is saying that you can take the span to effective depth ratio given in 23.2. That is valid for one-way slabs and one-way continuous beams. Now, for slabs with drops conforming to 31.22, we also seen that the slab drop panel should have minimum dimensions. Then only I can consider the larger thickness in my negative moment reinforcement requirements and so on. So, if you are providing drop panel in accordance with 31.22, or in other words, the dimensions of the drop should satisfy the minimum requirements given there. In that case, 23.2 can be directly applied, right? But if you're not providing drop panel, then you further multiply this and by 0.9. Okay. So, and also we need to use longer span shall be considered. And also for a flat slab cannot be less than 125. In fact, from fire resistance point of view, it is always better to have at least 125 mm thickness of the slab. Okay, so now what are these basic values? Up to 10 meters for a cantilever it is 7, for simply support it is 20, for continuous it is 26. I would say good number for even for a flat slab would be L by D ratio of 30 to start with. Okay, and that's why we are going to take anyway the slab is continuous, so we are going to take 26. And we have seen for one-way system there are so many modification factors are there, right? We look at modification factor for tension reinforcement, compression reinforcement, right? All those things that we talked about. So I'm here to, for simplify the process, I'm going to take a simplified modification factor of 25%. That's why I said 26 when I multiplied by 1.25, it'll work out to be 32 or so. But if you want to be a little bit more conservative, you can take an L by D ratio of 30 for a flat slab and then calculate the thickness. Okay. So I'm taking a modification factor of 1.25, lumped modification factor. So if I consider longer span, larger span, Ln, where here the clear longer span is 7,500 millimeter, we'll substitute that. I need a depth requirement of 231 millimeter. Okay, so this is the way you can come up with that for this. Okay, but if you're taking 26 without any modification factor, you may end up with higher value of the depth. Okay, so that is also okay. But we try to economize the slab thickness as much as possible without compromising the deflection requirements. Right. Now let us see what the Canadian code or an AC code says. AC code also says, okay, this is what I said. You take ln by 30, okay, as a good number for flat slab. Okay. Now what you see here is there is one more modification factor depending upon the grade of steel. Okay. So if I put Fy is equal to 415, this ratio works out to be 1. 415 by 1000 is 0.415 plus 0.6 is 1. Okay. And the code is actually what is it saying is, it is if Fy is going to be larger, then my rebar spacing is going to be longer, because when I use high grade steel, my area requirement will be less, then I will end up putting steel at a larger space, right? So that is the reason this is coming in the numerator. If I am, let's say I'm taking 500, then this value will become 1.1. Then when you divide it, this 30 will become 1.1. Basically, it basically it's like a reduction factor, right? Similarly, there is one more thing. Depending upon what kind of width of the drop panel and the depth of the drop panel, it is going to stiffen it up. If I have larger dimensions of the drop panel, the code is also saying that, okay, somehow I have to account for this. Okay, this factor is greater than 1. Okay, so you see here when you have larger drop panel, then 30 becomes 32, 33, 34, depending upon what I have, right? So that is the advantage. Okay. So similarly, when you have a low grade steel, again this number becomes more. So when you have a low grade steel, then you end up putting closer spacing of rebar. Your deflections are going to be lesser. Okay, from crack arresting and stuff like that, it is going to be better. So that is the reason the code recognizes this. So for flat slab, you take ln by 30 and then you apply some modification. That's why I said in the previous slide, L by 30 is a good value for a flat slab system to start with. So if you substitute that, if you assume drop panel to be, let's say, extending 1.5 meter from column center, and also the drop is going to have a thickness of d by 2, then if you see the longer span is going to be 8000 minus 500, which is 7500 millimeter, and xd is the distance from the face of the column to the edge of the drop panel. Okay, and in this case, basically, xd is the distance from the face of the column to the edge of the. So basically, this. Okay. So this is the total edge. Okay, in this case, 1500. We are having 500 by 500. So this distance is going to be 250. When you subtract it, xd works out to be 1250. And we should also take the value as less than ln. There is one more condition, right? So if you substitute all these values, this works out to be 1 by 2, and this works out to be again 1.5. So if you substitute all of them, you find that the thickness requirement should be greater than 236.5. So that's what it is. If you go back to the previous one, in a quick calculation, what we did, this is 231. Okay, they are very close. So you can see we can take like this. So including your clear cover requirement for slab is 15 mm plus some reinforcement cover. When you do it, a good round number of 250 mm can be selected for this particular span. Okay, so 250 mm we have arrived at from deflection control point of view. Now let us say drop panel. So drop panel, we need to have a minimum extension of 1/6 center to center. So let's see in the shorter direction, that means 6000 by 6, it should extend by 1000 millimeter on either side. And in the longer direction, it should extend by 1333 millimeter. But we have provided 1500 mm, so which is good. Okay. And also the thickness of the drop projection is 125 mm in this case, which is greater than 1/4 of the thickness of the slab. What is the 1/4 of the thickness of the slab? 250 mm is the thickness of slab. So 250 by 4 is basically your thickness of your projection should be at least greater than 1/4 the thickness of the slab. So the entire thickness, so the dimensions of drop panel, what we have provided is satisfying the minimum requirement. So I can take a larger depth of, so 125 mm plus 250 mm for my depth calculation. So the overall depth in my negative moment reinforcement is going to be 250 plus 125, which is 375, not just 250. If these dimensions of drop is not satisfying, then the depth have to be kept taken as 250 only. Okay, that is it. Now edge beam. So we need to, it's a good practice in a flat slab system to have an edge beam. Okay, that will help in reducing the deflections. So the edge beam must have a beam stiffness parameter of alpha b greater than 0.8 to provide favorable effect on minimum thickness requirement. Now, if I'm assuming a 250 mm width and 600 mm depth, I'm assuming, okay, to make sure that, at least on the edges of the building, you need to have this edge beam just to stiffen it up in a case of a flat slab flat plate system. So then the moment of inertia of this flange section is working out to be 6.329 into 10 to the power 9. Okay, and so this is the way that we have come up with, and these are the dimensions that we are talking about, right? From edge to edge is about, from center line of the edge to edges, you get about 6,000, and then when you do the calculations for moment of inertia, it works out to be 6.329. Now again, we have discussed this. Okay, so this distance is going to extend, okay, which is 125. So in the same way, that is also going to get, sorry, so this is going to be, yeah, 225, right? So that is the reason. So if you look at it, so this say another 225 goes, the overall dimension works out to be 250 plus whatever the distance that we have looked at. So this flange width works out to be 500 and the overall depth is 600. So when you do your moment of inertia calculation, we work out to be 6.329. And for slab, now we have in the edge panel direction. So if you see here, that's what we are seeing. And you see here, this is the slab that is going to be starting from here to here. Okay, this is the slab that, but this, what is the width that we are talking about? 3,250 or 4,250. So and thickness is 250. So for the slab also, basically what are they doing? We are calculating the relative stiffness between the edge beam and the slab. Okay, now we are looking at the edge beam, right? So that is the reason the width of the slab is only, I'm taking 3,250. Okay, on the other side it is going to be 4,250, right? So you take in the shorter direction, I'm having moment of inertia 4.238. That is when I use width of 3,250. In the longer direction, when I use a width of 4,250, I work out to be 5.539 into 10 to the power. So this we are going to use in your stiffness parameters, which is IB by IS. So when you substitute for shorter direction, I get 1.5, which is greater than 0.8. For longer direction, again, I get 1.14, which is greater than 0.8. So these beams are going to quite effectively create that extra stiffness, and it is going to be helpful and will have an effect on minimum thickness required. Okay. So next question is to calculate the effective depth. Okay, so now we calculated the thickness of the slab. We made sure the edge beams are having adequate stiffness that will have a favorable effect in reducing the deflections. Next step is to find what is the effective depth that can be used in your calculation. Now you see the slab is bending in two directions, right? So you are going to have two drop. Okay, so this probably two D short, and this is D long. Okay, so now these are the bars. Now the longer direction bending is actually perpendicular to the section that what we are seeing. So these are your longitudinal bars that are running along the longitudinal longer direction. These are running on shorter direction. Okay. So what should be the, now we have two layers of steel, right? So what should be the thickness of the, or the effective depth for the slab in the longitudinal direction? 250 mm, 20 mm cover I am taking, and I'm assuming that 16 mm bars I'm using. So it's going to be 250 minus 20 minus 16 by 2, which is 222 millimeter. Now for the same drop panel, what is it we do? Drop panel thickness is 375. Now the clear cover is 20, and again if I'm using 16 mm bar, then the depth, effective depth for drop panel is 347. Now you see, for the shorter direction, a longer direction, we want to, moments are going to be larger. That is the reason we put reinforcement in the longer direction at the bottom, right? In the shorter direction, now I have to use this 222 minus the 16. For example, if I'm measuring from here, this distance I have calculated D long. What will be D short? D long minus 1 diameter of this bar. Okay, that's what we are taking here, which is 206 millimeter, and 347 minus 16 works out to be 331 millimeter. These are the effective depths to be considered in the longer and shorter direction. Now let us calculate the loads. Okay, self height of the slab is, if I am taking 0.25, 25 times 0.25 works out to be 6.25 kilometer per meter square. Superimposed dead load we have taken as 2.5 kilometer per meter square, that is already given. Live load is given as 3 kilometer per meter square. So total factored load is, when I add all of them, 11.75, and I multiply by 1.5 to get a load of 17.63 kilometer per meter square. Now we are also having a drop panel. So that is going to create an additional factored load, and the thickness is 125 mm. So 25 times 0.125 multiplied by 1.5 factor, you get 4.69 kilonewton per meter square. So if you look at, this is the overall loading that we are getting. Okay. So you see this is 17.63 multiplied by 8. Okay. Which is going to be 141 kilonewton per meter. Okay. This is for the longer direction. Okay. And this is for a longer direction. Right. For the drop panel, 4.69 multiplied by 3, that works out to be 14.1 kilonewton per meter. On either side you have, right, 1.5, 1. And you get this load. Now let us say relative stiffness parameters. So our goal is to now find the relative stiffness parameters. Okay, now we are getting into this tables. Okay, and to use the tables, of course, we have to get TA by TB value. Now what is TA? TA is measured from the center line to this edge, because we are talking about drop panel with a drop. So the TA is working out to be how much? 125 plus 125, which is going to be equal to 250, and moment of inertia of column is 500 by 500, so it is going to be h cube by 12. So if you substitute the numbers, you get moment of inertia as this, and h by hc, we have done clear center to center height of the column is 3500, clear distance is 3125. So if you take the ratio, it is 1.12, and TA we have seen that as 250, and TB is only from center line to the top, which is 125. So you get the ratio of, for below column as 2. For above, you have to take the reverse. So if you take the reverse, it is 0.5. Okay. So using this TA by TB value and H by HC value, and we can go back and calculate your user tables that are given there, and find out what are these stiffness parameters. So stiffness parameters is, for TA by T equal to 2, when your H by H is, in H by H in this case is 1.12. So we have to do interpolation between this column and this column, and when you do that, you get KAB value, which is from A to B is 5.65, because it's in between this, right? So it's going to be 5.65. So again, when you substitute that, KAB times EC times IC by H works out to be 8.407 into 10 to the power 6. Just to numerics, we just plug in the value that we had previously calculated. Important parameters to use appropriate table. Okay, so in fact, this is not in SP16. So these are the table that are given in your line book, or you can also refer the AC code book, where it gives you these tables. Okay, so you can take this value, and now that we have found out this k values, and carryover factor also similar between this epochs will be 0.548. And similarly, we do that for column below also for this support. Now, when you look at it, now TA by TB value will be reverse, which is going to be equal to 0.5, 1 by 2. So again, we go back and use these values between zero point 0.4 and zero point 0.6. If you take this double interpolation, then you find that KBA value is 5.04. When you substitute all the values, you get KC factor as 8.035 into 10 to the power 6. They are nearly same because they are square columns, dimensions are not changing much, and carryover factor is 0.61. Okay, so you see here, carryover factor varies from here to here, 0.6. You have to do double interpolation. When you do that, you get a value of 0.61. Now I got stiffness parameter, I got my carryover factor. Now let's see for inequivalent frame. And for exterior columns, the long span H beam is going to act as a torsional member with a torsional constant. So now I need to calculate this torsional constant. What are the dimensions of this? 250 by 600, and this outer edge is also going to be going by 250. Okay. So this is as per the dimensions guideline that are given in the code, right? So for this, now I need to calculate C parameter. C parameter, we said it is going to come from this. Okay, I divide this L section into two rectangles. Okay, now if you see here, we have already discussed. I need to divide this by like this. This as one rectangle and this as another rectangle. Okay, then if you substitute that, we see 250 by 225 cube by 3 times 1 minus 0.63 times 2 multiplied by 250, and when you substitute these values, you get your C factor is 5.047 into 10 to the power 9 millimeter per foot. Just this is a sectional property for torsion. Okay, something similar to your polar mount definition, right? So in KT, then we have got the stiffness parameters 9 EC into C by L2 into 1 minus C2 by L2 whole cube. When you substitute that, you get the values. So everything now you see finally the stiffness parameters are expressed in terms of EC. Now the EC everywhere it will get cancelled. Now you can have EC for column can be different than that of beam, but if everything is same, elastic modulus of concrete for both, if I'm using same strength, then everything will get cancelled, right? So for interior columns, same thing. We are going to take cross section of torsional member as shown in this figure, 500 by 370. Okay, that is the width of the column and the depth of the drop panel. Okay, so that is what we are going to take that as a torsional member. Then again, we calculate your stiffness parameters for interior column. KT is working out to be 12.65 into 10 to the power 6 EC. Okay, so though there is no beam, okay, you have to, this is a flat slab, right? So though there is no beam that is running, what we are saying is we are considering the part of the beam, the slab is going to act like a torsion member, right? So that is what we are doing here. Now, equivalent column stiffness we have seen, it is going to be summation of Kc divided by 1 plus summation of Kc by Kt, and summation of Kc we have calculated 8.4 plus 8.03735 into 10 to the power 6, and Kt we calculated for exterior column is 13.78. So you see here this equivalent column stiffness works out to be 1 point. Substitute that, you get 7.507 times 10 to the power 6. Similarly, I do that for internal column and you get this values. Now you see we have got now stiffness parameters for columns. Now next step is to slab stiffness constants and fixed end moment coefficient. Now tables in AC 3C 318 can be used. Now this is actually applicable for L1 by 6 of 1.13 meter with a drop panel of only 1.13 meter. But what is the drop panel width that we have provided on one side? Actually, total width is 3 meter, but one side width, if you look at it, it is only 1.5 meter. So what I do is I cannot use this table directly. So what I'm going to do is I'm going to the load whatever it was there, I'm going to convert them into a only width of 1.13 meter. So it's some simplification that I'm doing so that I can ready-made use a table that is already available rather than I go ahead and derive these parameters. So what I'm going to do is I'm going to just convert this load, which is acting over a width of 1.5 meter to for the table value that is already developed for 1.13 meter. So I'm going to slightly increase the load, convert the area that is a load that is acting 1.5 meter to 1.13 meter. So that's what we're doing. So if you look at this again table, depending upon C1 and N1 and C1, Cn2 by L2, we can calculate the stiffness parameters. And these are the table that we have already discussed for slab beam element. So if you look at, in this case, we have square columns. So Cf1 equal to Cn1, Cf2 is equal to Cn2, and if you substitute Cn1 by L1, I get 0.083, Cn2 by L2 as 0.0625. So I get these values. So I go ahead and calculate my stiffness parameter for a flat slab system. And anyway, everywhere I'm taking that it is going to be loaded uniformly. So that is the reason I'm getting between this value. Okay. I have to do interpolation between this and this because my parameters are this, right? So I get factor, stiffness factor for near end as for 5.944 and for carryover factor is 0.595 and fixed end moment coefficient is slightly higher value of 0.0931, okay, for uniform, because we are saying that everywhere it is loaded, okay. Okay, now for an additional load due to drop panel, the table gives moment coefficients for partial loadings of 0.2 L1 with B minus A equal to zero point 0.2. Okay, so in this case, we worked out drop panel load as 14.1 kilonewton per meter. That applies over a length of, again, why I am taking 3 meters? In the transverse direction, I have a width of 3 meters. Though it is acting over a distance of 1.5 meter, the transverse direction it is 3 meters. So this I am saying that though this is applying over a distance of 1.5 meter, but the table that what we have is actually for 0.2 L1 only. So I'm going to just amplify this 14.4 to act over a distance of only 0.2 L1. So what I do, I multiply 14.1 multiplied by 0.25 by zero point 0.2. So the equivalent load for a shorter dimension over which it is acting is 17.63 kilonewton per meter. So we can go ahead and use this table, see the figure in this tables. So if you go ahead and look at these values, it is basically 14.1, which is acting at a distance of 1500, has been converted into an equivalent load of 17.63 that is acting over a distance of only 1.2 meter. So just a simplification that we are doing so that we can use a ready-made table that are already available. Again, if you go back to table 11.6 in your book, okay. So these tables have been recreated from AC code and for standard boundary conditions. So if you take Cn1 by L1 and Cn2 by L2 as 0.0625, then you get your moment coefficients as 0.0166, and for drop panel at far end it is 0.0019. Okay, so now we got all these values. The slab stiffness parameter is now KNF into EC into LS by L1, and you plug in all the values. Moment of inertia is 8 meter width times 250 cube by 12. This is this, and Ks we worked out to be 5.944 EC, and substitute everything, and you can express in terms of EC like that. And then now I got the slab stiffness parameters, column stiffness parameters, carryover factors, and fixed end moment coefficients. Now we got all the parameters. We are going to go ahead and do moment distribution analysis. Okay, so the properties of the equivalent frame for analysis by moment distribution method is can be done like this. Okay, so that's what we're going to do. So the specified live load again is less than 3/4 of the dead load, which is 8.75 kilonewton per meter square. So we don't need to do pattern load. So if we just to do single loading pattern, it is sufficient with full factored dead load plus live loads on all spans. So that is what this is the loading that we are going to consider. And 17.63 kilonewton per meter square. But why I need to multiply by 8 meter? We are doing an interior span. The width L2 is 8 meters. So if you substitute that, you get 141 kilonewton per meter. And similarly, the loading for the drop panel is 14.1 kilonewton per meter. Okay, these are the loading that we have. So fixed end moment coefficients are what? So if you substitute this, we are not using 14.1. Why are we using this? Is totally 17.63, right? Because now we have converted this into an equivalent depth of 0.21, right? So fixed end moment coefficients are 484.5 kilonewton meter. So once you do all these things, so you see here the fixed end moment coefficients have been found out, and stiffness of the column is 10.31 for this location. Similarly, everywhere it is same because same stiffness parameters, right? And similarly, equivalent column stiffness is 7.507 into 10 to the power of 6 EC. For this one, it is 7.148. This interior ones are going to be same. Exterior ones are going to be same. So exterior ones this and this, interior one this and going to be same. Now similarly, distribution factor can be calculated as 0.579 for this joint. Okay, and we are looking at only this. Okay, the slab. Okay, because we are designing a slab. Okay, so that's why in the joint you have an equivalent column means this also the stiffness of the equivalent column is going to be now 1 minus 0.579, right? So we are not concerned about that at this point of time because we are designing only the slab. Okay, so that's why I'm taking distribution factor as 0.579, and for this slab on the left side it is 0.371, and the edge stiffness for this joint is going to be 0.57. Similarly, carrier factors are all 0.595. And for all the spans, now we got the fixed end moments negative, positive, negative, positive, negative, positive, because negative WL square by 12 plus WL square by 12, right? So, like that, we got these values 484.5. Now we have to basically balance all the joints, right? Now, why is that I'm balancing only with 280? How do you balance? Fixed end moment has to equal and opposite moment I have to apply. But here I'm not applying plus 484, I'm applying only plus 280 point. Why is that so? Because we are concerned about what is the distribution factor is 0.57. So I take 0.579 multiplied by plus 484.5. That is the moment that I'm applying as a balancing. Similarly on this side also. Then what you do? You go ahead and carry over this to the far end, and then you keep repeating this exercise. So when do you stop this exercise? When your carryover moments are going to be very, very small. Okay. Here we are talking the range of 2 kilonewton meters. So we say that we have sufficiently balanced and carryover, and the carryover value is becoming very, very small. So kind of the joints have reached its final position. Then you sum all the moments, you find that working out to be negative 227. So that means at this location you get a negative 227, and at this location I'm getting 582.5, 582, and this 519, and here 519, here 582, and here 227. So these are the distribution of the moments that we got. Okay, these are all the support moments at the slab location only. Okay. Now, the finally what we can do, so we get your left and right moment like this. Similarly, the shear also we can calculate if it is uniformly distributed load like this with same moments, and we know that it is going to be shear is going to be 141, it is 6 by 2 plus 14.1 times 1.5, that works out to be 444 kilonewton. So, but if your loading is, if your moments are not going to be symmetrical, we know how to calculate your positive moment, okay, from simple free body diagram of the moments, okay. So, if you have this kind of thing, you know this moment and you know this moment, and you know what is the load that is acting on it. So, you can calculate from free body diagram what are the reactions, and we can calculate what is the moment at the positive moment at the center. Okay, so this is, let's say, ml, this is mr. Okay, and if you know the loading, and from simple free body diagram we can get your positive moment levels. These are all, I think, structural analysis. I don't want to spend too much time. So once we get your slab moment at the supports, we can get the positive moment also. The positive moment, for example, at this location works out to be 258.5. At this location, it works out to be 131 kilometers. Now, you see, this is the moment that is acting over the entire width. So, all we have done in this example is to find out what is the longitudinal distribution of the moments, okay, at all the locations. At this location, if you look at it, it is going to be negative 227. At this location, if you look at it, it is 582.5. At this location, if you look at it, it is 519. At this location, 519 again. At this location, 582. At this location, 227. At this location, positive 258 point. At this location, 131. Here also it is going to be 130. 131. 258.5. So like this, we got all the moments. These are all longitudinal distribution of the moments. Now again in the transverse direction, we need to do one more step. How much should go to column strip, how much should go to middle strip, that is going to be exactly same like what we done in the previous direct design method example, right? So with that, we can conclude this module. This module, we discuss the basics of equivalent frame method and what is an equivalent frame and how these stiffness, carryover, and fixed end moment values are going to be different because the stiffness is changing. It's the sections are not prismatic. We discussed about that, and we discussed about what is an equivalent column and how its stiffness was derived. And also we carried out one flat slab example with the top panel, right, using equivalent frame method. And what did we get? We got only longitudinal distribution amount. Again, transverse distribution also you need to do, and that is same as that of what we have done for direct design, right? So with that, I would like to thank you, and I would also like to acknowledge the help of my student, Mr. Ranjit. He is an MTech student, for helping me with all the slide preparation